So it's very sad that we no longer see Professor Nambu and talk to him these days. As everybody knows, Professor Nambu has been one of the greatest theoretical physicists of our time. He was an idol of my generation. He contributed so much to transform or bring particle physics to the present-day standard model. He further introduced the string theory, which will be the main ingredient of particle physics of future generation. So we no longer have the special privilege of having a great man around us. Last time when I saw him was in the early June 7th, in the hospital of Osaka. This day was a Sunday, and I wanted to come to Osaka and see Professor Nambu. I used to see him around once a month in these days. It turned out on the previous day, June 6th, he had serious pain in his heart, which looked like an after effect of a heart attack he suffered before. And he was kept in an ICU. So I was not sure if I could see him, but it turned out I was allowed to enter the ICU room. Professor Nambu seemed recovered from the pain of the day before and was in a good condition and spirit. He was smiling with his family. When first he saw me, he mentioned the word 0-point life, pointing to himself. He was making a joke out of the health condition of himself. I think this was one of the happy moments during his last fight against illness. I stayed for a few hours and went back to Tokyo. So I want to keep the memory of this scene of ICU for the rest of my life. Now let me turn to the discussion of physics. About 5 years ago, together with collaborators, Oguri and Tachikawa, I have found some curious phenomenon in string theory, appearance of exotic new symmetry of the theory. This is now called as moonshine phenomenon as under intensive study. Professor Nambu was curious to hear about this story. However, there was no chance to tell him the details. So thus today, I'd like to give you a brief introduction to moonshine phenomena, which may possibly play an interesting role in string theory in the future. I think concerning the phenomenon of moonshine, I think we are more or less familiar with the so-called monstrous moonshine phenomenon. So here, I'm looking at the so-called J function. J function is something which has a special invariance under the modular transformation. So J function is a function of Q. Q is e to the 2 pi I tau. Imaginary tau is positive, it's upper half plane. And tau is transformed into A tau plus B divided by theta plus t. ABCD is SL to Z matrix. And it turns out when we impose this condition that this function is invariant under the modular transformation, SL to Z transformation, this is the only solution. So J function is determined to have this form. Actually, there are other solutions, but the other solution is just the meromorphic function of J function. So this is essentially unique. So we have one over Q term, a constant term, and Q to the 1 term, square term, cube term, etc. And there's a very strange expansion quotient. So Q to the 1's first term is 196,884, and Q to the square term 21493760, and etc. And it goes to very large numbers very quickly. But it turns out there is a very strange rule among these expansion quotients. So Q expansion quotient of J function are decomposed into a sum of dimensions of reducible representation of the monster group M. So 196,884 is 1 plus 196,883, and it's known somehow this number 196,883 is the size of the smallest reducible representation of the monster group. So here's a list of some of the smaller representation of the monster group. So in the expansion quotient, we notice the presence of these numbers. So the next expansion quotient was 21493760. 21493760, so it's this number. But now this number is decomposed into 1 plus 196,6883, 21296876, 21296876, so it's here. So it's a combination of these three terms. Then if you go to q to the cube term, then we find this quotient 864,29970, and which is decomposed now into a sum of these numbers. And this, so here we have a new one, 8426929326, 84269326. So somehow there is a very strange situation here that we seem to find the decomposition of all these big numbers into a set of big numbers, and with a quotient, with a relatively small quotient, quotient 1 or quotient 2 or quotient 3. So it turns out in the expansion quotient of the J function, dimension of some irreducible representation of monster group appeared. The monster group is the biggest, largest sporadic discrete groups. There are sort of discrete groups which goes keep increasing and goes to infinity. But beside that, there are discrete groups which are isolated. And so these are the sporadic discrete groups, and the monster group is the biggest one of this kind. And the order of monster group is 10 to the 53. So there are as many elements as 10 to the 53. It's like the number of atoms in the universe, something like that. It's an enormously large group. So this observation, the strange relationship between the modular form and isolated discrete group was pointed out by Mackay, 1978. So it's called the Mackay observation. So this was actually, this was quite, how to say, quite a surprise, I think, at the time. So because we do not expect any simple relationship between the modular functions and the isolated discrete groups. They are completely different objects. There is zero overlap between the mathematical area covered by the isolated discrete groups and the mathematical area covered by the modular functions. So this was quite a surprise. To be precise, actually, it turns out the q to the zeroth term, 744, is more or less irrelevant to the problem. So we can get rid of it. 744 is eliminated. So then we have an expansion of q to the n is -1, 1, 2, 3, etc. Cn q to the n. And it seems there is this representation of the monster group. So that is Vn at each level n. It's reducible. Vn is reducible. It's a sum of a finite number of reducible representations. So if you take a trace of identity operator, unit matrix of the size of the dimension Vn, we get quotient Cn. So we reproduce this J function. And actually, this expansion is not quite unique because there is always one in as a group element. There is always one as a number. So 196,884 could be 1 plus 1 plus 1 plus 1 plus 1, 196,000 times 884 times. So the decomposition which I just wrote down is a possible decomposition, but it's not unique. In order to have a unique decomposition, we can construct the so-called Mackay-Thompson series. So instead of the element 1, identity element, we consider an arbitrary element G of the monster group and compute the trace of this quantity and construct a new series, JG of tau. So this depends only on the conjugacy class of G. So corresponding to each conjugacy class of the monster group, then I can construct a new sort of series, which is very much like a J function. Now one is replaced by the element G. So here, trace of a representation Vn of G denote the character of the group element G in the representation Vn. This depends on the conjugacy class G of M. So if Mackay-Thompson series is known for all conjugacy classes, the composition of Vn into reducible representations become uniquely determined. So there is no ambiguity. So series, and it turned out, so people at the time computed, there are 196 conjugacy classes of monster group. People computed it and have they constructed the unique decomposition of J function. So phenomenon of monstrous moonshine has been solved basically mathematically in the early 1990s using the technology of vertex operator algebra. However, the solution itself doesn't convey very much intuitive understanding of why such a strange phenomenon takes place. So we still do not have a simple or physical explanation of this phenomenon. So this is the, in a sense, it's first generation monstrous moonshine, first generation moonshine phenomenon. But now we seem to have seen the appearance in the second generation of the moonshine phenomenon. So let's see. Let me first explain what was first discovered recently, and then attempt to try to understand what it means. So instead of the J function, we consider an elliptic genus of K3 surface. So I think many of you are familiar with the elliptic surface. So, K3 surface. So probably I may not have to explain details. So let's consider string theory compactified on K3 surface. K3 surface is a complex two-dimensional hyperkähler manifold. It possesses SU2 holonomy and holomorphic 2 form, and ubiquitous. It appears everywhere in string theory. So it's something which is very familiar to us. And it is well known, string theory on K3 has an n is equal to 4 superconformal symmetry with a central charge C is equal to 6, which contains SU2 level 1 affine symmetry. Now, instead of modular J function, we consider the elliptic genus of K3 surface. Elliptic genus describe the topological invariance of the target manifold and count the number of BPS states in the theory. Using worksheet variables, it is written as, so elliptic genus of, let's say, K3 is given by the trace of the string theory Hilbert space, left moving Hilbert space times the right moving Hilbert space, and -1 to the fermion number, left moving fermion number, right moving fermion number, and J3 is the Cartan generator of AC2, and Q to the L0 are the Virasoro operators, and C over 24 is C is the central charge. Actually, so this is 6. So C 6 over 24 is 1/4, and Q bar L0 bar minus quarter. So here L0 denotes the zero mode of the Virasoro operators, and if left and right left moving fermion numbers. J03 is the Cartan generator of affine AC2. In elliptic genus, right moving sector is frozen to supersymmetric ground states. And if you look at this formula, right moving sector is -1 to the F, and there is nothing here. So this refers only to the left moving sector. So -1 to the fermion number, and Q bar L0 bar minus constant. So that is the structure, -1 to the fermion number and E to the Hamiltonian. And this is the structure of the index theory. So index theory says only the lowest energy states survive under such construction. All the higher contribution from the higher states appear in pairs between fermions and bosons. And -1 to the F assigns opposite sign to bosons and fermions. So they all cancel. So the contribution from the right moving sector of the Hilbert space everywhere cancel except the ground state. And the ground state energy is actually, turns out, it's just exactly compensated by this factor. So in the end, this factor disappears. So if we evaluate this elliptic surface, and then it looks like the right moving degrees of freedom completely disappear. Only we are left with the left moving degrees of freedom. In the case of left moving degrees of freedom, -1 to the F and Q to the L0, so there is a tendency to cancel. But because we have inserted this operator, and this operator, depending on the spin or isospin of the bosonic state or fermionic state, excited state, they supply a different weight factor. So the cancellation doesn't take place in the left moving sector. So in the left moving sector, we really have to add all the contributions, contributions to the string theory Hilbert space. Let's see, weighted by these weight factors. And in general, it's difficult. I think not in many cases the elliptic genus are computable. But it turns out in the case of K3, we managed to do the computation. And the method we use is we use the Gepner model, so-called. So the K3 surface has a moduli. So at a particular point in the modular space, the theory is soluble. These are the so-called Gepner points. And we can compute at different points. And then it turns out, then we get the same expression, independent of the choice of the moduli. Because we are computing this quantity, which is topological. So non-topological quantities are modular dependent, but the topological quantity is independent of moduli. So you can take a particular Gepner model at a particular point in the modular space and go through the computation. Then we get the correct result. And this is the result we have obtained at the time. The thetas are Jacobi theta functions, theta to z divided by theta to 0, and etc. So when z is set to 0, then we find that this quantity is just 8 times 3 is 24, and 24 is the Euler number of K3 surface. So this is the final result. Elliptic genus at z is equal to 0 gives you back the Euler number of the manifold. So we want to see how the Hilbert space, left-moving Hilbert space HL in elliptic genus decompose into reducible representations of n is equal to 4 superconformal algebra. So we know this expression, then we want to see how this expression is decomposed into representation of n is equal to 4 superconformal algebra. So for that, we have to know the character formulas for various representation of n is equal to 4 superconformal algebra. So let me just explain that. So n is, if you look at n is equal to 4 superconformal algebra, the Cartan generators of this algebra given by the zero mode of the Virasoro, L0, and zero mode of affine AC2. So the eigenvalue of L0 is H. The eigenvalue of spin operator is L. So we have the representation which is leveled by the value of H, the Virasoro eigenvalue, and L, the spin of the ground state. There are two different types of representation in C is equal to 6 superconformal algebra. This C is equal to 6 is a case relevant to K3 surface. So in the Ramon sector, there are BPS, so-called BPS representation. There are non-BPS representation. BPS representation in space-time gives rise to massless particles. So sometimes we call them as massless representation. Non-BPS representations describe space-time massive degrees of freedom. So we call them as massive representations. So basically, the BPS representations are the smallest energy, lowest energy representations. So H is equal to 1/4. And this is in the case of Ramon in the sector. And the spin, there are two different spins. L is equal to 0 representation, L is equal to 1/2 representation. And non-BPS massive representations is higher. And the value of H is not discretized. So this is a continuous representation. BPS are the discrete representations. The character of the representation is given by this formula. So this again is very close to the index of the representation. But so when z is equal to 0, there is a cancellation, and only the ground state contributes. And in the case of BPS representation, there is the asymmetry in the ground state. So there is this index survives. The index is non-zero, non-vanishing. In the case of massive representation, indices vanishes. And when, so we have index is equal to -1 to the q to the l. And the index of BPS representation, spin 0 representation is singlet. So index is 1, spin 1/2 representation is doublet. And by convention, spin 1/2 representations have a minus sign. Yeah. In the case of non-BPS representations, the index vanishes. The states all paired up and cancel. Now then, so this is the index. So the full character, we have to do the computation. And it turns out BPS representation has somewhat complicated expression. So H is 1/4, it's okay. So there are two BPS representations, L is equal to 0 and 1. So let me just look at the L is equal to 0 case, which is sort of basic. And it turns out there is a theta 1 squared theta cube term times this mu function. And mu function is an infinite series, but with a rather complicated structure. And in the case of non-BPS representations, basically we have just this part times arbitrary power of h. H is bigger than quota. So actually, so this structure is, let's see, level k is equal to 1, n is equal to 4 superconformal algebra has a realization by 4 free bosons and 4 free fermions. 4 free bosons and 4 free fermions, just the Fock space gives this contribution. So if there are no singular vectors, there is no complication. So this is it. So in the case of non-BPS representation, this is the character representation. And in the case of BPS representations, there's a complication. And the function mu is a typical example of the so-called Mochthota function. And what happens is that when you try to see how this transforms under SL2Z modular transformation, then you get a very strange expression. I'm not going to write it down, but it's well known that these objects, these are sometimes called the log sum or upper function or Mochthota function, of an anomalous transformation law and has been very difficult to handle. People didn't quite know how to handle this object. But recently, there are developments in understanding the nature of Mochthota functions due to some mathematicians. Zwogers, he introduced a method of regularization. This is very much like the one regularization used in physics. And when we regularize the expression, then the modular transformation property, Mochthota function, is improved. And they are turned into the so-called Jacobi forms. They transform like Jacobi theta functions. And recently, there has been some sort of understanding this regularization, the sort of physical understanding of regularization, and in particular, in the case of path integral formulation, the modular property is sort of imposed by construction. Then in that case, the path integral evaluation of the system automatically, the answer automatically is incorporated in the regularization, the regularized Mochthota function. So let us make a decomposition of elliptic genus into a sum of characters of NX4 representations. So we know now the elliptic genus of K3, and we know the BPS character representation character formula with this mu function, Mochthota function. And we have the character of non-BPS representation. So we have everybody. We know these expressions. So we want to expand. So these are expansion bases. We want to expand the elliptic genus in terms of these objects and find out what are the expansion coefficients. So elliptic genus is a function of tau and z. Tau is the modulus of the torus, and z is the local coordinate of the torus. And also these n is equal to 4 characters are functions of tau and z. So because we know that this quantity has n is equal to 4 superconformal algebra, it should be expanded in terms of these basis functions. So the expansion coefficient just depends only on tau. Yes?
In the sum there, you're including n equals 0?
It's delicate. It's like 744. So, okay, I'll show you what happens. So A0 is special. So let's forget for the moment. So the sum is 1, and also there is a contribution 0. And let's concentrate on the expansion coefficients A1, A2, A3, A4, etc. So we have these numbers. It's okay, positive. I think positivity is probably, it's not obvious. Should be integral, because this is the, well, I think so. The elliptic genus is expanded in terms of these characters of various representations. I think these are integers, but the sign is not obvious. But in any case, what happens is that if you do the expansion, we can do this just by the series expansion tau and z, and compare both sides and derive this expression. So 45 to 31, 770, 22, 77, etc. Now, so there is a surprise. A dimension of reduced representation of the massive group M24 seemed to appear in this expansion. So 45 is here, 231 is here, 770 is here, 2277, 2277, 5796, 5796, 13915. So we don't have 13915, but 13915 can be decomposed into the sum. And then we have 395, 3520. And let's see, 3843 can be decomposed into some of these terms. So, well, this was quite a surprise. So something similar to the case of monstrous moonshine appears here. So, well, so instead of J function, bring in the let's say elliptic genus of some may not be K3, but in this case we have used K3. Then expansion, the basis of the expansion is in the case of monstrous moonshine, it was just a Q series. But in this case, we know that there is this n-equals superconformal of a system. Arc works on the system. Then the excitation of the system is always assembled into representation of these n-equals superconformal algebra. So these are the basis of the expansion. So if you do that expansion, then well, we have a very sort of similar phenomenon. So we are finding the dimension of representation of massive group M24. We didn't expect, well, actually we expected a little bit of there is some, in a different context, there is some work by mathematician on the relevance of M23 for K3 surface. So we thought there might be a connection to the massive group, but actually there is really no basic understanding at all as yet why M24 appear here. M24 is a subgroup of S24, permutation group of 24 objects. Its order is given by 10 to the 9, so it's much smaller than monster. M24 is known for its many interesting arithmetic properties, and in particular, it is intimately tied to the Golay code of efficient error corrections. So the size of the group is monster is very large, Conway is very large, and Mathieu is medium. And and they are embedded into this pattern. Yeah, coming back to the question, the Greg's question. So A0 is subtle. A0 is negative, -1. And in this comparison, A0 is ignored. We are comparing A1, A2, A3, etc. with the dimension M24. So that is a bit like the zeroth order term in monstrous moonshine, 744. But we don't know the precise relationship. Okay. So this is the moonshine conjecture. Expansion coefficient of K3 elliptic genus into n is for characters are given by the sum of dimensions representation of massive group M24. In the case of monstrous moonshine, in order to have a rigorous decomposition, we need a Mackay-Thompson series. So instead of identity element, we insert the arbitrary group element and take the trace. And we can do the similar thing. So then this decomposition is sort of made unique, and we can test this conjecture in a more rigorous manner. So we did this construction, and so AN is now decomposed into the various representations, dimension various representations, and the expansion coefficients. And here the conjecture is CRN should be all positive integers. N is equal to 0, there is -1. So that's a different problem. So CNR has to be, for any n, CNR has to be positive integer. So this is a conjecture. And we could compute n is equal to up to n is equal to 500 or 1,000, something like that. This is feasible by PC. And so this is the, let's see, up to n is equal to 35 or something like that. So these are the dimension representations. So the n is equal to 1, that the first level, we have so at n is equal to 1, we had the 45. At n is equal to 2, we had 231. At n is equal to 3, we had 770, etc. Actually, there are columns here which I cannot squeeze in. So if you go to a higher and higher level, let's see. So these coefficients increase very fast, but you see that all the coefficients are positive and endure.
Is there any rule as to which representations?
That's again a big question. And let's see. The question is, for instance, why 45 appears first? Could be 23. There are smaller in the case of monster, the smallest representation appears first, as it turns out, and the bigger and bigger. So they are all sort of ordered. But in the case of M24, 45, 231, 770, and we don't have any simple rule in this structure. So now this conjecture is now proved by mathematical induction. So up to a certain level of n, suppose it's okay, all these numbers are positive integers. Then using the mathematical induction, we can say for any n, then this is true. See, the expansion coefficients are positive integers. How much? 50 minutes. So in that sense, we have now proof. So this is proved. The K3 elliptic genus is expanded into this series, and the expansion coefficients are positive integers. Unfortunately, the proof so far did not provide much insight into the nature of massive moonshine. the situation looks a bit like the case of Monsters Moonshine. 24 of M24 is certainly the Euler number of K3, and M24 permutes these homology classes. There are, however, various indications that string theory on K3 cannot have such a high symmetry as M24. Instead, the total Hilbert space, instead of the total Hilbert space, BRS subset of the theory may possibly possess an enhanced symmetry. It will be interesting looked into the algebraic structures BPS states to explain Matthew Moonshine, but this hasn't been done yet. So Matthew Moonshine exists at the intersection of various things: string theory, K3 surface, Moch modular forms, discrete groups, etc. So it seems an interesting mixture of physics and mathematics. Recently, there have been some intense interest in exploring new types of moonshine phenomena other than this Matthew Moonshine. Already several types of new moonshine phenomena has been discovered. We have umbral moonshine, Chen, Duncan, Hovey, fermions on 24-dimensional lattice, spin 7 manifold, and etc. Let's see, do they show it? I think I have 10 minutes left. Oh, actually, it's not. Yeah. So let me make a few comments about umbral moonshine. Umbral moonshine has a mysterious relationship to the so-called Niemeyer lattice. It is known in 24 dimensions. There are 23 or 24 self-dual lattices, depending on whether you include Ridge lattice or not. It is given by the combination root lattices of AD type together with appropriate weight vectors so that the lattice becomes self-dual. Simplest ones are the following. So we have A1 type root lattice. SU2 root lattice is one-dimensional. So A1 to the 24th power is a 24-dimensional lattice. And we have to add suitable weight vectors so that we have a unimodular lattice. And the second example, A2 to the 12. A2 is SU3 root lattice, two-dimensional, 12 power of that. This is the Niemeyer lattice number 2. Niemeyer lattice number 3, let's say, is A3 to the 8th, etc. Automorphism group of Niemeyer lattices are M24 times, let's see, it has this structure. Automorphism group of lattice contains a wire group of root lattice. So SU2 has a wire group Z2 is 2 to the 24. The next one is the automorphism group M12 times 3 factorial 12. Then case to the 3 case, G times 4 factorial to the 8, and etc. So if we just get rid of this symmetry factor coming from the roots, then we get M24. So the first one in this series corresponds to the Matthew Moonshine, as it turns out. So this is a group of a moonshine phenomenon. So it's possible to construct this series of models, moonshine phenomenon, starting from the Matthew Moonshine, and the discrete group, which acts as a monster group, as a moonshine group, is given by automorphism group of lattice divided by the wire group of root lattice. So this is a very interesting generalization. Starting from the Matthew Moonshine, then you can generate the series. But there is a little bit of difficulty in the geometrical understanding of this umbral moonshine. We don't quite understand how to interpret this object. Recently, we came up with some idea to try to understand umbra moonshine from somewhat different point of view, but we are still in the middle of work, so maybe we shouldn't discuss it at the moment. So I think I'm running out of time. So moonshine's symmetries recently discovered in string theory are still very mysterious and not well understood, but we may encounter many more surprises in the near future. Thank you very much.
Is there a simple way to characterize the subgroup of S24 that constitutes M24? Some rule for forming the subgroup?
I'm sorry, I don't know. Some experts, I think, will be familiar.
Read Mathieu.
You mentioned something quickly about the ADEs, the client singularities and the blend spaces. Could you elaborate on something besides A1 and A2? How did those come in?
In this construction, the Niemeyer lattice, you are allowed to use ADE type 3 algebras. And basically, A to the, well, basically up to, you take a combination so that altogether there is a 24 dimensions, and the size of the unit lattice is equal to 1. And I think your question is, let's see, A to the AN to the power type. Presume there are ALE type solutions, and so yeah. Actually, I want to ask you the question. So there are solutions, just A type, product of A types, a solution for the product of D types, also maybe the product of E types. Is there a solution guaranteed to exist for the mixture of them? Is it? This is all the claim by Hitchen.
You barely mentioned your recent paper, but I hope I can ask you a question about it anyway. And I haven't had time to study it terribly carefully, but using the n equals 4 Liouville approach that
Liouville theory, yeah.
I can certainly imagine that it's possible to obtain some of the Mach modular forms or Jacobi forms of umbral moonshine, but I was wondering whether you saw any sign of the group action actually acting on the conformal field theory.
Group action of the
umbral groups.
Of the moonshine groups.
Yeah.
No. This is, well, there's some kind of duality here. And, well, umbral moonshine in the ordinary understanding is you go to larger and larger spaces rather instead of K3. Higher level of SU2 group is used. And well, and here you find a mapping of such a system to our. I think I should talk with you. Yeah,